Hi everyone, we will start in 5 minutes. Hello everybody, we will start soon. We are going to start in few minutes. Thank you for joining. We are starting in few minutes. Still a lot of people joining. We are waiting and we start in 1 or 2 minutes. Still a lot of people are continue to join. So let's wait 1 or 2 minutes and we will start. So we are going to start in 1 minute. We will start very soon. Okay, I believe we can start our workshop. Welcome everyone. Thank you for joining us for today's webinar. My name is Alex Akulin, Technical Chief at Aviarshare. Our company is a Cadence channel partner in Eastern Europe, Middle Asia, and Caucasus. Just a little announcement. All attendees will be muted. If you have any questions during the presentations, please type them into the Q&A section. It's in the gray box on the right side. We will answer them at the end of the presentation. If you want your question to be private, not to be shown to all attendees, please mention it in your question. The recording of this webinar will be sent to you in about a week. This webinar will be presented by Andrew Wallace from Cadence. Andy Wallace first went on to design RF and microwave components for test and measurement equipment at Marconi Instruments, covering 10 MHz to 50 GHz frequencies. From 2001, he became the European Technical Application Engineer for AWR company for technical support, product development, and training for Microwave Office, moving over to UK country manager in 2003. Acquisition of AWR by Cadence found Andy as senior sales account executive, later moving to senior system sales executive, focusing on all Cadence system products. Today, Andy works as account technical executive. Over to you, Andy. Hello.
Good morning, good afternoon, good evening to everyone joining us. Thank you for taking the time today. And thank you, Alex and the Cadence team, for asking me to present this webinar. A quick bit of background on myself. Alex explained my history, but I was previously a design engineer with Marconi for 10 years before coming to AWR for almost 20 years. We were acquired by Cadence in 2020. And I cover a lot of the system tools. That includes the AWR tools, Microwave Office and VSS, Visual System Simulator. The electromagnetic tools would go with those, but also the Cadence PCB offering, that's Allegro. The signal integrity and power integrity tool called Sigrity. Clarity, which is a 3D electromagnetic engine. We'll touch on that a little bit today in today's webinar. Celsius, the thermal tool. Again, we'll mention that today. But also a PCB inspection tool called InspectAL. So quite a broad range of system products in the Cadence portfolio. Today we have a busy agenda. I'll outline a little bit about Microwave Office, MW Office software as a software tool and its links to the electromagnetic engines. And then we'll dive straight into the extraction. This is the way of taking a schematic layout into the electromagnetic world automatically. That extraction makes it an incredibly powerful part of the design flow to look at simulation effects that we don't normally cover with schematic elements. I'm an ex-engineer, as I mentioned, so we'll be doing a lot of live design examples that I'll show you. I'll run them simulation real time on my machine, and you'll see the simulation results appear as they would on your own computers. We've got many examples there, from filters and low noise amplifiers through to a multi-layer board, a MMIC chip, that's a monolithic microwave integrated circuit, all the way through to 3D bond wire extraction, and perhaps we'll touch on thermal. Now, today's webinar is focused on the aerospace and defense industry, looking specifically at the requirement to shrink designs, be it perhaps for small drone devices or similar, and the idea that as you shrink the design, we end up generating problems that are quite often missed in the simulation world. There's also the requirement of many of these systems to have antennas. So our second section will touch on the antenna analysis, both of a single patch antenna to show the approach, and indeed of the phased array synthesis and simulation, before we conclude and take questions and answers. I expect this webinar to last about 50 minutes, and we'll leave some time for the questions. So Microwave Office is a structure of software platform and the electromagnetic tools. We are referring to a design suite of software, the AWR Microwave Office product, that is a single C++ database, and it's architected very different to many other software platforms. It means that we can work in the electrical circuit schematic world, or we could drop into the systems budget analysis world. We could work in the electromagnetic environments, and all of those are sub-circuits in the same design view. The layout, be it 2D or 3-dimensional, is all part of the same schematic entry. And that's critical at RF and microwave frequencies because connection lines aren't just simple DC connections. They are, in fact, in most cases, part of the electrical design in terms of transmission line width or impedance. We'll look at the simulation capability within these tools, typically frequency domain in linear or non-linear analysis, non-linear required for power amplifiers, for mixers, for anything that saturates. But also the linear tool is incredibly fast, and that will allow us to design low noise amplifiers, filters, splitters, and other passive networks. I'll show you the effect of that single database layout in a moment, but those together mean that we have an exceptional user experience. We're generating the layout as we go. Now, of course, that layout can be exported as GDS2 in the case of chip design, as DXF for PCB, or as Gerber file format to produce them and manufacture the PCB boards. We're going to be focusing quite a bit today on the EM extraction side of this flow to show you how we can take that layout automatically into the electromagnetic tool. Now, I mentioned the AWR design platform. This includes Axiom, that's a planar electromagnetic tool, Analyst, a 3D FEM, finite element method solver, and also the Visual Systems Simulator. That's a sample time domain systems block diagram tool that sits all inside the same platform. Since the acquisition by Cadence, we have integrated their 3D EM tool. That's a product called Clarity, and their thermal tool, a 3D FEM solver once again called Celsius. And they excel at FEM simulation because they're able to distribute the mesh generation of the problem as well as the solving. So they will address very large board structures, very large electrical or mechanical structures in the EM or thermal worlds. The beauty of these tools sitting side by side is that we can design from the system budget analysis, perhaps designing a communications link. We can drop into the circuit level design in the center of the screen here, and we can design the physical board with the actual vendor library component parts and the layout. We can drop back into the system world to look at test benches and excite with real modulation signals, for example, radar or 5G. And then finally, we can drop into the EM world, that's the focus of this webinar today, to look at analysis perhaps of cross-coupling that was unexpected, maybe of antennas and radiation patterns in the 3D or the planar 2D EM world. We have many approaches to the electromagnetic simulation tool within inside the platform. For circuit level simulation, we have very straightforward cross-sectional solvers. These are used in the electrical world, in the frequency domain tool, to look at coupling across tracks that run parallel, perhaps on the board layer, or maybe through a board structure. That means that we're able to use a simple cross-sectional solve, and that's a very fast simulation method looking through the board stack. It does assume those board lines go on forever. So there is an approximation there that there are no changes in the dielectric layers and no changes in direction of the traces. Once we come away from that, we move towards the 3D planar world, and this is using typically a method of moments tool. We have two within the AWR platform. EMSite is an on-grid solver. It is fantastic at filters, at matching networks, at patch antennas, and so forth. And we're taking the circuit layout for verification in that electromagnetic world. When we need to start adding thickness of metal and perhaps an open boundary solver for antennas, then Axiom is the preferred tool. That's unlike EMSite. Axiom is an off-grid electromagnetic solver. The mesh is generated regardless of the design. It gets exactly the right transmission line and conductor material shapes. And that's ideal for looking at curved corners and for PCB import. And although it's a planar tool, we can also do thickness of metal. And that becomes important when we're looking at the thickness, for example, with the spiral inductor, where there is parallel plate capacitance due to the height of the thickness of the metal, alongside the positional capacitance due to the number of turns and the tightness of that gap. When the problem becomes truly three-dimensional, so if you have waveguide, if you have connected to board transitions, if you have bond wires or arbitrary enclosures, or radomes, then we really do need a 3D tool. And today there are two approaches in the Microwave Office suite. The original AWR platform called Analyst, that's a 3D FEM solver, and Clarity. Clarity is also a 3D FEM solver, but at the moment we're doing some beta testing on a finite difference time domain approach with inside Clarity. Now, I've mentioned earlier on that Clarity will mesh the problem across multiple compute cores, as well as solve across multiple compute cores. So it's faster, as far as I'm aware, than any other traditional 3D FEM solver on the market, including Analyst. So it depends on the type of problem as to which EMU engine you use. The topics today will talk about EM extraction from the circuit design, and that can go into planar electromagnetic tools like EMsight and Axiom. It can also go into 3D EM tools like Analyst and Clarity if it's a 3D issue, or indeed into even thermal tools today. Cadence have a tool called Celsius that is a thermal 3D FEM solver, and we can export the layout generated by the schematic diagram into the thermal engine. Again, I have a slide on that later on. So specifically then for Axiom, the 3D planar tool, this is method of moments. It's open boundary, so we solve without metal walls around the element. That's great for antennas and antenna radiation patterns. On the top left corner of this picture, you can see a beamforming antenna radiation pattern that's been generated from the software. And in the center, quite a fancy Sierpinski type antenna. All possible because they're planar and flat in nature. PCBs by definition are planar and flat in nature, so that's the best solver to use for that approach. It is an off-grid solver, so we mesh the problems that are sent to the EM tool, and it's fully integrated into the circuit level simulator Microwave Office. We can do optimization here, we can annotate and view the fields and currents, we can do parametric sweeps and studies. If the issue is a 3D problem, I've mentioned Analyst and Clarity. They're both accessible from exactly the same flow. And these are really looking at on and off chip passives, any 3D structures like a connector to board transition, perhaps a waveguide structure, bond wires inside the package, as you can see in a moment on the next slide. And again, this is integrated into the Microwave Office tool. We even have parameterized 3D elements that you can use and drop into the schematic design, along with some vendor encrypted components like connectors inside Clarity that come with a complete and accurate design as a 3D file that we use from the vendor manufacturers. Again, parametric studies, post-processing, and the ability to run over compute farms mean that that's a very fast 3D electromagnetic tool. And finally, the same extract flow I'm about to show you would work into the thermal world as well. So we can take the design from the schematics entry. That design is 2 and 3D because of the single database. And we can copy that across into a thermal tool. I'll show you a similar design to this one working inside the software in one of my examples. In this case, we have 3D bond wires. We have gallium arsenide transistor chips here, and you can see that they all heat with the RF power. The flow into the thermal tool is identical to that from the planar and 3D electromagnetic software. So let's look then inside the software at the actual extraction flow that I've mentioned and how it works. In the presentation that we'll share with you, I'll leave these slides behind, but I'm an ex-engineer and I love to demonstrate the software. So what I'm going to do is hopefully open up the design. You should be able to see the screen just now, and I'll check with my colleagues that are on the chat with me that screen has changed. Here we have Microwave Office, and it's a circuit level simulator that we have just here, and it's very easy to drive. If I right click here on a new schematic diagram, we can generate a new schematic diagram, and from the elements tree we start to populate that with microstrip strip-line models. As we do so, these models aren't just electrical devices. Let's lose these for a moment in the background, but they have 2D and 3D layout associated with them. So the moment that I look at the 2D and the 3D image of this single C++ object, you can see that it sits there at the correct size. If we change the schematic data, we update the layout. And if we come into the layout and double click and update the length of the line and the width of the line, you see immediately that the electrical schematic values are updating. It's not synchronization. There's no layout versus schematic checking needed here. It is one C++ object that has views electrically in the 2D view and in the 3D view. So very, very easy to drag and drop those down. If I do that and start to build up a stub circuit, just as you saw a moment ago, I'm dragging in a microstrip T line, an output transmission line and a stub. You'll see just here that we have then effectively a 2D and 3D layout for this, this design. That is giving us the ability to consider the layout as part of the electrical simulation. And when we generate a graph just here, let's turn off this one for a moment. We simulate and we run that simulation and look at the results from the electrical world. Now we have a wonderful tool inside Microwave Office where you can add any of the parameter values to a tuning scroll bar. You pick up the screwdriver, you pick up the width and the length of this item, you'll see that those parameters are added. And as I move the length and reduce that down, you should see the simulation results update. If I were to grab the actual item, and you'll see that when we let go of the slide bar, the schematic values update too. So that's real-time simulation running, as you can see on the web video just there, giving us the answers. I'm just going to restore that to 10 millimeters as that's the basis now of our next approach. Taking this design, what we need to do is send it out to the electromagnetic tool. And it's very simple to do so. We have the substrate definition here for the microstrip lines, but I'm going to drop into the scripts menu, use a script to generate the stack up that goes with this. And when we do so, you can see that we end up with a stack up that copies the microstrip substrate, but adds perhaps air and a board material above, perhaps if there is the electromagnetic world, and also this extract block. That extract block allows us to go round the electrical items, select those electrical items, right click into their properties. Sorry, it was on a different screen, and enable this extraction tick box. If we enable that extraction tick box, then we end up immediately with the items being sent to the electromagnetic engine. So I've done that just here, and when we hit simulate, off goes the software. It copies the schematic diagram into the EM world. It goes away and it runs the electromagnetic simulation, and it comes back with the results from a planar method of moments from exactly that same design. That's something that will give us some answers, plotting the trace on the graph right over the top of what we had previously. Now, although this computer is actually a 10-core machine with dual threads, it could run 20 cores or virtual cores. I'm running just on 8 threads. We're doing adaptive frequency sweep. Just here, you can see that we've got various frequency points running, and that will give us some answers across the frequency band and plot our new trace. So the actual method to take this schematic design, take that across to the electromagnetic world is very straightforward. We are drawing the schematic diagram. We use a script to generate the stack up and the extract block, and then we take the elements and we link them via the extract block into the EM world. When we hit simulate, the software will go away and simulate that now in a method of moments tool, having meshed the design. Going to cancel that for a moment. I've got many more frequency points than I need. I don't need the answers to that just now. So with the block off, we end up with the electrical simulation. And just in here now, I've got another design. That second design looks identical, but it has got the stack up and extract block enabled. And when we turn on the trace from this simulation, you can see that when we run through the EM tool, we actually end up with, in this case, the right frequency points, a slightly different response. Now that's because we're looking at the radiation from the end of the stub. And in terms of the stack up of material, we might be looking at the layer of air and perhaps a lid above the box. So you can see immediately if we were to lower the lid down and make that much closer to our track, re-hit simulate, then our transmission line resonant frequency is likely to change because of the position of that lid. And you'll see that our pink trace now has jumped from the left of the original to the right. That's an effect of the lid. Let's go back and make that much further away once again. Now, also, when we start to shrink designs, we've got some clever items here that we can use. Instead of a standard transmission line, what I've got in this case is an M-trace element. That M-trace element in the layout allows me to route the item back round on itself. So I'm keeping the length fixed to 10 millimeters, but bending it back on itself. It should still be the same transmission line performance, but of course now there is coupling in these traces that the electrical design does not take into account. When we hit simulate, the method that takes place is that we copy that schematic into the electromagnetic world. You see that it's just updated the copy. We put it onto the board material in 3D space. We mesh that, and the mesh was generated in the background. And that mesh is solved with the 3D planar method of moments tool. The S parameter files brought back, and we end up with the results in the schematic simulation traces. So really, this idea of bending the transmission line, folding it back on itself, gives us quite different results in terms of frequency points. And you can see just here, if I mark them, our original was at 5 or 4.9 gigahertz. The fact that we're folding it back is now 400 megahertz higher, about 10% in difference. And that's purely because of that coupling from the trace line. So it's important to use this flow. To repeat that once again, I'm taking the electrical schematic design that generates the layout automatically. With the extract block, the extraction copies the design into the EM world and does an EM simulation. And just to prove that it is copying dynamically, let's double click and change this line just here. In fact, let's go back and make it a straight line. I'm going to go back in and show you this one. This is why it should have been here. Let's fold it back on itself this way. That folding back, when we hit simulate, is copied into the electromagnetic tool. The mesh is generated, and I expect this will change in frequency once again from 5.3 gigahertz, changed in depth of notch there because of the way that the coupling is taking place. So this extraction flow is a very straightforward method to use. Let's drop back into the slides. I showed you in the first instance a very straightforward T-junction, but this extraction is critical when you start to get complex board designs. So my second example here is a filter extraction. We've used a filter synthesis tool to generate a hairpin filter. And if we drop into the software just now, let's find that one. 2 moments, this one here. You can see that that schematic diagram is what's responsible for generating the layout. If I come in here and turn off the schematic elements, it is the schematic diagram that is generating the electrical layout. That's in 2 and 3D views. And when we simulate in the linear simulator, we have quite a fast simulation result. Now, in this case, we've actually done one other step in between. This is a bend in the structure, this section here. We don't have a very good electrical model for that. So we have an EM design for that bend that has been meshed and simulated in the EM tool in its own right. So that is a standalone bend that we've included. Now that bend means that there is signal coupled back against itself. And you can see in the graph that there is quite a difference between the original schematic diagram, this is the electrical models, versus the design that has the electromagnetic results for the bend. Again, this is quite a big shift in corner frequency, going from 5.5 gigahertz all the way up to 5.6 gigahertz. So 100 megahertz difference perhaps in that corner frequency. Now that's quite a quick and dirty way of looking at the design just with the bend. What I want to do is extract the whole filter. So in this case, our extract block is pointing to the Axiom tool. I've mentioned earlier on we could get to 3D EM or EM thermal approaches. So in this case, we're going out to Axiom. And what it will do is it will copy that design into the electromagnetic world, like we have here. It will take that into the substrate definition and mesh that and solve it in the electromagnetic world. Once again, let's hit go and look at the results. So once again, even a small difference from the EM bend, the electrical bend that's done, we now have a complete filter that's solved and simulated in the electromagnetic world, with a response that I would trust. And that's because we're folding things in nice and tight, and because coupling is going on between the circuit elements that perhaps we're not simulating. So critical to use this planar electromagnetic tool within the design flow. Not only can we send out circuit diagram elements, but we can also send out other parts of the board design too. And this is critical, I think, when you start to include things like ground plane or wire holes, enclosure cavities and walls. So this next example, once again, I'll leave the slide in the presentation, is one that we ship with the software. In fact, they all are. Let me go and open this full screen for you to view as we're demonstrating. After the webinar, you can get access to these examples under File Open Example. And this one is one that ships in the software, as in fact they all are. If we type in NNA, you can find there's a 5 GHz low noise amplifier that ships with the software. That's the example that I'm showing you here today. Every example that we ship comes with design notes, and in the design notes at the top of the project tree, we explain what we're trying to show. And in fact, this one is talking about, in particular, the axiom extraction and how we do that. So I'm going to run this in two ways. The first simulation is going to run this design. We have low noise amplifier with its signal gain of about 10 dBs, designed to be centered at 5 GHz. That's the circuit electrical models. And that's what we have from, in this case, an S parameter data file, but also the matching circuits that have been designed around that. It's a very fast linear simulation, so you'd expect some very quick results. But as an ex-engineer, I've got suspicions that although this center line is designed by the schematic tool, the extra ground plane and board elements, in fact we can see them in 3D here, will have effect on the design. So what I want to do is take my design, copy it as a hierarchical subcircuit, and use one extraction block. That extraction block extracts all of the metalwork. So when we see here, anything in red will be taken to the electromagnetic tool automatically. The ports are assigned, the port de-embedding is done automatically. Any coupling or any radiation that goes on is picked up in the electromagnetic tool. The circuit elements are simulated back in the circuit level design schematic. So we do include the electrical connections of those as well. So it will still be an amplifier with gain, with the attenuation and matching that you have here, but with the electromagnetic results added. And when we switch on that extract block and resimulate, we go away and we simulate in a 3D electromagnetic world. It's the 3D planar. So here's the copy of the design. There's the structure in the 3D microstrip world and the mesh that was used. And we get a very fast simulation result from that design. And that was pre-simulated. So what I'm going to do during this particular call is if I force resimulation, you'll see the idea of the simulation time it takes to run this problem. Sorry, the simulation window was on another screen. It is a very, very fast process. And when I hit go, you can see that within a few seconds, we have the electromagnetic results now. I don't have time to go make coffee. I don't have time to go and take a lunch break. Electromagnetic engines are being used in the design flow, and that's critical. We're now picking up coupling, we're picking up radiation losses, and more importantly to me as a design engineer, what I thought I'd made as a 5 GHz amplifier has now shifted in frequency. Again, it's about 10% out. So that shows the importance of using electromagnetic tools in the design flow. Those have been simple designs. They've been on PCB stack of material with one layer, FR4 microstrip Rogers material, perhaps from microwave type design. But this extraction flow works in an identical way for multi-layer boards, as you'd expect. This particular design, once again, I leave the slide here, but I'll jump into the software to show you it working. It's a multi-layer, low temperature co-fired ceramic design. And if we look at the 3D picture, hopefully you can clearly see there, it's about 6 or 7 layers. And in fact, what we have is on the top surface, we have a very similar low noise amplifier with matching components, but a buried filter. That filter is buried inside the board stack. Now that's a strip line type filter inside the layers of board material. but I've been quite a bad design engineer. I've put some of my matching network overlapping that filter underneath that's some distance inside the board stack. In the electrical world, when we design this circuitry, of course, we design it with the filter and the amplifier as completely isolated elements, and we look at the responses of the two individual items. We have the performance of the low noise amplifier, the performance of the filter, and when we bolt them back to back, we get what we expect to be the final design. Looks nice and clean, looks well behaved, and we manufacture that and find there's actually quite a difference in the manufacturing measured results compared to simulation. Because Microwave Office in the Cadence Dissolve Suite has this extraction flow capability, we could take that structure, we could extract it into the EM world. You can see it here. We can even do some clever things like simplify the number of layers. We've got exactly the same layer depth, but now only treated as 2 or 3 separate layers, because that speeds up the electromagnetics. The ports are now all automatically de-embedded. The S-parameter results are generated from this structure, and once again, as an engineer, I'll simulate that. We get some real results. Now, it's very nice to compare the electromagnetic, if I freeze that graph, with the non-electromagnetic. So I simply turn off the extract block. You can see rather worryingly, we get some very strange visual artifacts because of that filter stub overlap with the bandpass filter buried inside. Now it's quite close to real life measurements, and as you can see, our expected filter bandwidth is actually much less than I would have hoped from the design. So this design in flow using the electromagnetic engine is really important, and it does need to be predicted. We can design around it, and perhaps in this case I could flip those stub lines and put them the other side and not overlap the buried bandpass filter if there was space to do so. That was a simple PCB, but what if you were designing gallium arsenide or gallium nitride, silicon germanium chips? To the Microwave Office tool, that's simply another process design kit. And by process design kit, I mean that we've started the software with design layers, units, and coloring appropriate to a chip design tool. So if I jump into that example, here you can see that we've got a circuit level design. There's a gallium arsenide chip. So here's my transistor, here's my matching network, and in this case, the matching network might be matching. In fact, that was the device. Sorry, let's go down across here. Matching network. The input network might be a sub-circuit that is now built with spiral inductors via holes and printed items that are on the gallium arsenide chip. This has the layout generated by the schematic diagram that looks like that. Radial stub filtering on the input and multi-layer gallium arsenide, gallium nitride type design techniques. We can export this as GDS2 to make the design. And once again, when we simulate in the schematic diagram, we have a very fast linear simulation, non-linear if we have non-linear devices, and you see the response here of the non-linear simulation in this case using the active devices. Now in this case, once again, at a top level of hierarchy, I'm going to extract the whole design. Now again, to give you some idea, if we look at that extraction block, it's extracting the whole amplifier. This is all the metalwork minus the active devices. The transistors have ports. We're going to send that to the method of moment solver. So that will go away and mesh this off grid. So you can see the triangles where we need them and the rectangles where we can get away with them. In fact, this is quite a coarse grid. I'd not recommend this. This is actually just for speed in the demonstration today, but I'd recommend at least 3 cells across the lines. But even so, we get a good result from the electromagnetic engine. Why is that important? We have a lot of the biasing chokes linking and very close to the RF transmission lines. We have the interstage biasing close to the first and the output stage coupling, and they will all interact. The electrical diagram doesn't pick any of that up, the EM tool does. And when we hit simulate, once again, that was a pre-stored answer. Let me do this and force it to run fresh. So I pre-simulated this today before the webinar. When I hit go, we see this run through the electromagnetic engine, and the time that it takes to run that as a problem in the method of moments tool. I'm only using 8 cores. I could make this twice as fast on my computer if I used all of them. We're jumping around with what we call AFS, adaptive frequency sweep. And that technique is to look at some of the front end frequency points, some at the back end, test some in the middle, and validate equation fits. And if we're happy with that equation fit and that validated data, we estimate and predict from equations the electromagnetic results. We can very simply switch off AFS, the automatic frequency sweep. But it's a nice way to have a quick look-see at the simulation results and what's going on. And once again, we don't really have time to go away for coffee. This should all be part of the design flow. We've now got quite a complex design there with metallization of the input and the output. We're simulating at multiple frequency points, and you can see that within just a few moments, as a live simulation on this webinar, I'm not cheating, nothing's pre-simulated. I'm not using a server farm or the cloud. It's being run on my compute machine. We can see some very quick answers to the design popping through on the simulation tool. That will predict all of that interstage coupling. And in this case, I don't know if you saw down on the bottom left graph, we lost a great deal of our amplifier bandwidth. There it is, it's finished. So that's the simulation time for this rather complex, complete metallization design. This is the result that we get. And if I freeze that on the graph, go back to our circuit level models, very, very fast results, of course, from circuit, but very inaccurate in terms of bandwidth and gain that we're predicting. So I do stress once again how critical and important it is to use this extraction approach to get designs right first time. More so when you're starting to shrink designs down as elements and structures, be it drones, be it remote vehicles, be it any type of printed circuit board where you're trying to reduce surface area or volume of the PCB or the electrical design. So I hope that's made some sense with the EM extraction flow. Let's drop back into the slides for a moment. I now want to move on to this concept with exactly the same flow technique, but moving out to the 3D electromagnetic engine. And today in our Cadence world, we have 2 FEM engines, Analyst and Clarity. In fact, you can run them both side by side in the platform if you have license and wish to do so to compare results. And they do give identical results in the simulation world within 0.01, 0.05 of a dB. So very accurate results from the 2 different approaches. But the flow is identical. So once again, I'd like to show you this rather than talk to a slide. Here's our design. Remember, the electrical design elements are generated in the schematic layout. All I drew manually here was the heatsink block tower that sits under my chip. We have 2 technologies here. We have printed circuit board surface mount components for the output matching filter. And we have a MESFET design, all designed again electrically in the schematic diagram. And around that, connecting the 2, we have bond wire elements. These are very simple electrical models, although they're quite advanced, these bond wires, and they have JEDEC standards behind them in either 3 or 4 bond wire segments. And when we drop them down electrically, we place them in the 2D layout view. Now, the issue is that when we simulate with the linear and non-linear tools, let's again drag across, there's my harmonic balance engine running, we have a very clean design. And that's clean because in this case, the electrical bond wires are completely isolated electrically in the schematic diagram. In this case, that's a 3D problem. And what I'm going to do is suggest that we use exactly the same extraction flow. That extraction block is now linked to just the bond wires. So you'll see down here the segments that we're taking, just the bond wires, not the flat MESFET or the elements. But this time, the difference is that I've selected Analyst, the 3D FEM solver. I could send this to Axiom, but it's a 3D problem. And it's a 3D problem because we have a bond wire going through air across the height of dielectric substrate that could also couple. Once again, what the flow does is it takes the design that I've marked, it will generate an extraction that's copying those elements, puts on the ports automatically, but this time we're in a 3D world. And when we generate the mesh, that mesh is generated across both the metallization, the dielectric, and if I make sure I turn it on, a 3D engine will also solve all of the air volume above the design. So now we've got quite a complex tetrahedra mesh to solve. Not flat triangles and squares like Axiom, but 3D tetrahedra. And once again, as an ex-engineer, I don't like cheating. Let's hit simulate. That's again been already done, so let's force it to run from scratch. Even at that level of intensity and what we have here in terms of the information, it's quite a few unknowns. We're going to go away and mesh this design and solve it. We'll set that going. And we have something like 10,000 unknown counts in terms of the mesh, just under 10,000. So that gives you an idea of the complexity of the problem for this part of the design. I'll hit simulate and start that running. And what you'll see on the graph is the previous results. I'll show you again live during the webinar how long it takes. But the results show a marked difference between the amplifier and matching network gain when we take it into electromagnetic world to check any coupling between those bond wires. Now, the approach in this instance, ladies and gentlemen, is that we go round a loop. This is adaptive mesh refinement, like any other 3D electromagnetic tool. We do an initial mesh, solve the problem, and have an answer, then refine the mesh once again and solve a second time. We compare those two mesh answers and see whether there's any difference. And we're trying to get this difference down to with below minus 20 dBs or thereabouts in terms of two simulation runs. This is now on the 6th iteration of solving that problem. So remember, we have something like 9,000 unknown cell elements in 3D volume. I'm solving on an 8-core laptop whilst I'm running this web seminar. I'm also talking to you today. And all of that is running in the background whilst using the machine for multiple applications. And within just a few minutes of me talking there, we've dropped below our error tolerance. That's a pass as far as the software is concerned. We do a final mesh, refine it once again and rerun that for one final check. And if that also drops below the error tolerance, then we agree that the results are valid and we plot that trace as an accurate, a dynamic and up-to-date result for the 3D problem in this instance. So that's a 3D FEM solve in real time, run on my machine. There we go, it's finished, and the results that come from that. And once again, if we freeze that trace, we could switch off the extract block and drop back into the circuit level simulation, and you'll see the results from that immediately. So there is a marked difference in terms of coupling. In this case, we actually appear to get a little bit more power from the device, or perhaps more gain, maybe because we're taking into account coupling away from ground plane or lack of loss that the electrical models were predicting, that in fact in the electromagnetic world we have the absolute correct material. So it's critical to do that in the 3D world as well. Let's carry on with our slides. I mentioned that this is possible into the thermal engine. So far we've done an extraction into the electromagnetic world in 2D for Axiom and 3D for FEM. Let's look quite quickly at a thermal extraction. Now it's done in exactly the same way in the software. We have a circuit diagram. We have the layout that's generated for that. In this case, it's 4 active devices with their splitters. The only difference in this design is that in here, I've asked it to go and extract that design. If I turn this on, you can see it's picking up the amplifier chip, all of the metallization. That's what it's going to send in this case, not to the thermal tool, sorry, not to the electromagnetic tool, but to the thermal tool, because I chose Celsius in the pull down menu. Now, Celsius also needs the power table. That's something we calculate, and that power table tells us what the RF and DC power is in the tracks. And when we send it out to that tool, this does take 2 or 3 minutes. We're running short on webinar time, so I'll just show you the simulation results. We end up sending back the thermal profile, a quantitative profile picture with the temperatures shown back in the tool. We can slice through that design if we wish. Let's come in here and slice and look at how that temperature profile is across, in this case, a gallium arsenide, a gallium nitride chip, the heat radiating from the FET fingers. Those at the external edges are a lot cooler because of the grounding via. So that thermal extraction, the extract flow, is possible in the software suite too, at any level. It could be printed circuit boards. That is it if you're using the electromagnetic engine from the schematic as a starting point. Let's start to spend a few moments on antenna analysis and looking at the electromagnetic tool standalone. So again, I have the slides here. This is a built-in example in the software, and I prefer to show you it live in the tool rather than talk to a slide. Let me see if I can find the right design, this one here. So here's the software itself. It's a very easy design to put together. We literally, in the 2D world, we draw in the layout on the copper layers some shapes. We draw multiple shapes that we union together by selecting them and putting them and unioning those together. And then we can draw some cutouts there. So again, if I draw a shape here, copy and paste with Control-C, Control-V, pick up our shape and the two items that I want to subtract, we can subtract those away. So very quickly, I've drawn the structure that you see on the right-hand side. I've added to that structure under the Draw menu some shape modifiers to modify the length of the edge. And again, once that's specified, we can easily change that and change the size of the design. It needs to be sensible with my cutout, of course, but you can see that those shape modifiers work very nicely. So that's been done on the right-hand side here. I've taken those parameters for the length and width, and I've gone in and I've set them to be either tunable, but more importantly here, I've set them to optimize. So we have a 2D shape. We put on a port. It has a 3D view, of course. And what I've done is I've asked it to simulate in Axiom, the method of moments tool, simulate the design. But in this case, it's an antenna. So under the project tab, I right click here and ask it to add me annotation. And I'm going to add annotation for the 3D antenna picture. That's what you can see just here already added. That's generated here. Now this is a perfect microstrip design with perfect ground plane on the bottom side. That's why you see nothing underneath. But what I have is some 2D graphs on broadside gain versus frequency and the input match. I've drawn some optimization goals here. You simply right click on the optimization goal, pick the measurement, add the goal, and it appears on the screen. And once they're on the screen, you could even drag and drop and move these around physically and dynamically by moving them. Why have I done that? I want to optimize this antenna for a 5 gigahertz operation. So when I've got that graph and that trace defined, that structure already manufactured and proposed, I can now run the optimizer. We have multiple optimization methods, but in this case, we're on a grid, so I'm going to run the grid search. And what you'll see if I move these windows out the way is as we run the simulation, I hope that you can see that the antenna size is changing automatically by the optimizer. And within just a few moments, we find a solution that meets those antenna design goals. Again, this is running real time on my computer, ladies and gentlemen. It's only running on 8 cores. We're not doing anything clever. I could make it much faster. And that's real time simulation of multiple changes to multiple parameters in the optimization world. Because we had stop at minimum error when I stopped this design, we end up simulating and showing you the final result. So that's an optimized patch. In this case, we've moved the frequency to 5 gigahertz. Now, finally, in this webinar, I promised to mention the idea of phased array antennas. They could be based either on planar designs or on 3D designs. I mentioned the 3D tool. So very quickly, here's a pyramid horn that's been designed. Again, to give you an idea of simulation speed, I'll hit go. This is now 3D finite element solving. A pyramid horn that's been designed in the structure. We can import SAT files, IDIS files, step files. This is running in Analyst. It would run identically in Clarity, but actually be even faster still. And we go around this adaptive mesh sweep. And when it's finished, in fact, it's done. That's the first iteration finished. Now, I don't need, in this case, for the webinar to let that converge. It takes a few more minutes. We're running short on time today, but what you can see now is it's done 2 simulations of this design. We've annotated the 3D view, and we've got the cross-sectional cuts and solves for the structure on our graphs. They are grayed out because I stopped the simulation before convergence had finished. But the design was done with an electric and magnetic boundary, i.e. some symmetry, and you can see our quarter waveguide horn design here, but the radiation pattern with absolute quantitative directivity and radiation emissions powers. So finally on our slide deck, I mentioned that we could use the phased array wizard. This is built into the tool, and the idea is that we take a design, we can configure the phased array repetition of that design, and in the synthesis window look at the radiation pattern. We can play around with gain tapers or element failures. We can look at the response in 3D in the synthesis tool. This phased array generator would then allow us to play around with configurations, topologies, perhaps tapers, mathematically affecting the signal that is sent to each patch. And finally, we export that into the analysis tool. This is a planar array patch, so this is ideal for Axiom. So to finish the presentation today, again, I'd like to drop into that as an electrical design. Here it is. What I did was I used a phased array wizard. It sits down under the wizard's branch. That phased array wizard or the generator allows us to propose a structure, I don't know, 4x2, 4x3. And as we're doing that proposal, we can look at the antenna radiation pattern, steer the beam, but also look at applying mathematical tapers to see whether we can focus that energy on bore site. And in fact, in this case, I did a 4x4 array, and we can then simply go and generate the schematic layout that dumps it into Microwave Office as an Axiom problem. Once in Microwave Office, I've already done that in the background just here, it takes a few moments, we end up with a 4x4 array, the electrical ports all produced, and we can simulate that in the electromagnetic tool. But one clever thing here to add is that in the electromagnetic tool, we can excite it with a circuit level signal. Because Microwave Office is a circuit tool and an electromagnetic tool are one and the same piece of software, we have a real drive signal of 40 dBm going to each of these elements which affect the phase and magnitude. In fact, each of these is a repetition of, if I come down inside the feed network, a phase control module and an attenuation module controlled by the row in the index, row in the column index. And we simulate that in the electromagnetic world, and in this case use that EM sub-circuit. You can see the 16 antennas here, I hope, moving around from the EM results in the electrical world. So once again, rather than cheat, it's not pre-simulated. I'll hit simulate. You can see the speed of simulation in the webinar live for this type of level of integration. I'm running 8 cores. And what I've done in this case is I've set up the tuner to hijack the phi and the theta calculations to allow us to investigate some of the beam steering, but also some of the side lobe generation in the tool. So just to reiterate, we use the phased array wizard generator, sitting down under the wizard's branch to generate the array. It doesn't have to be rectangular like I have here. It could be circular. It could be an off-grid array. It doesn't have to be a patch. It could be whatever your underlying individual item is. And that could be quite a complicated design, perhaps on a PCB carrier. We use that, and we excite it with a circuit level signal. That circuit level signal is going to back annotate some phased array patterns, and we're going to annotate those then into the 3D view, the planar 3D view, once the simulation's finished. Now we're going to let that just finish simulation. I'll come back to that in a moment, as I say, to show you the real-time simulation. But just as a final slide, I wanted to show you that we have that phased array synthesis. This is the type of result you'll see in the simulation world, so that you have record of it in the presentation webinar slide deck. And we took that to an extreme, where we took the two of those modules, 4x4, so 16 elements, and multiplied them up into 32. We fed them from the schematic diagram. We actually took Microwave Office and used surface mount components on the rear side, and we started to analyze the radiation pattern and the side lobe loss of power because of the mechanics and the electrical items on the back. And we also tried exciting with 2 beams. So you can see the design there when we start to get complicated. It does take a bit longer. This is now into a few minutes of simulation time rather than something I can show live on the design. If we come back to our simulation result, where has it gone? We're sitting just here in a moment. That will pop through and show me the simulation answers for our design tool. So finishing off on the slides, I've shown you the microwave office structure, the axiom, the analyst, and in fact we can right click and choose clarity as the engine, all the electromagnetic tools as part of the design flow. We've worked through multiple technology approaches from mimic chip, PCB multi-layer. We've looked at 2 and 3D horns, and you can see now that the software has jumped back in onto full screen and hopefully shared. The results are very close to finishing. That took about 6 or 7 minutes on my computer while I'm also running the webinar. Now, I do want to point out that training is available, and ultimately we can eliminate costly errors, accelerate time to market, and meet our modern design trends, regardless of it all still being in simulation. So yes, a very powerful approach and tool. I'll give that just another minute to finish, but I'd like to invite Alex back at this stage to see whether we have any questions from today's webinar, and I'll jump back in once my simulation is complete and show you the results in just a moment. I'd like to thank you for your attention. Please do stay for the survey when we're done, and at this point I'd like to see if there are any questions from our team.
Okay, thank you, Andy. Yeah, please type your questions or comments into the Q&A box in the gray area. And if you don't want your question to be visible to all attendees, please mention this. And actually, following your kind presentation, I remember the story from my PCB engineering days. We designed PCB with embedded RF amplifiers, but later an unexperienced engineer routed the digital part, and at the final stage, he added copper sieving, a grid of small copper spots for DFM, design for manufacturing. Yes. And when we assembled and tested the board, the RF circuit failed because of the extra copper, which was not predicted. Simulation, I believe, would have saved us in this case.
Most definitely, Alex, most definitely.
Well, it looks like we have a few questions. First one, I can try to share it. Do you see it right now?
Yes.
Don't you think merging Clarity 3D solver with AWR's original method of momentum solver will confuse the end user?
I don't think so, no. It's a great question. Thank you for asking. Now this is finished, I just wanted to drop back into that and show you that, in fact, we've run that simulation. It is complete, and the tune tool allows us to electrically, in the schematic diagram, play around with the theta, phi, and direction of this beam steer. Of course, we could optimize that. The question about Clarity being integrated, no, not at all, because literally all we do in the software is we can right click on the EM structure. This is the 16 element array. We can set the simulator and we can choose which engine this is sent to. And it's down to the user to decide whether a planar tool is appropriate, whether a 3D tool is appropriate. And of course, Clarity, with the ability to run across a compute farm, I'm afraid does cost a bit more money. It does take longer in terms of simulation time. So there are benefits to the planar tool. If you wanted to replicate this design and have the answer in Clarity, you simply drag and drop the design. As simple as that. Mouse click, drag and drop. You right click, set the simulator, and we set this to be Clarity. The first thing you see is that is now in a 3D enclosure, because the 3D tool needs a 3D structure. And when I come in and mesh, as you saw earlier on, it will mesh with tetrahedra rather than flat triangles. So there is a beautiful way of running in both tools. If you wish, you can compare one to the other and you can look at the answers. One downside, of course, is Clarity is a third-party standalone piece of software. So it does need to fire up the software in the background. It does need to mesh it and then bring the answers back. And that's what you've seen happen here. Once again, live, I'm not cheating. It's meshed that full structure for us in 3D tetrahedra in a remote engine. So you get the beauty of both worlds. The speed, if the problem is planar, Alex, or the power and the ultimate accuracy, but at a cost, of course, if the structure is 3D.
Andy, I have heard that Cadence had embedded Clarity, this great 3D solver, to Virtuoso, to the tool of analog and RFIC design, integrated circuit design.
Yes.
So there is a new technology which allows to simulate the 3D IC constructions as well.
It's exactly the same platform, and we just talked to it from both original design cockpits. Yes.
Perfect, perfect. Then the next question is, I show it, where are the slides to go through for ourselves later? So will the slides be available?
I believe that the marketing team will certainly change these into PDF format and share them with the audience. So anybody that's registered today will get copies of the slides. Most of the projects that I've shown today, in fact, all of the projects that I've shown today, you'll be able to find for yourselves under File Open Example. If you search for keywords, you'll be able to find every one that I've shown. So, for example, the patch antenna is sitting there. The patch array that I finished with is sitting here. The low noise amplifier, if I type LNA, the first initial design is also built into the tool. So you'll have them in the software if you have a trial license or the software already installed on site.
So if we generate the trial license for the customer, or we provide the license for the student, he could find all these projects available in the library, right?
They certainly can, yes. Yes, indeed.
Great, great. Then the next question is minimum requirements for hardware to run the tools mentioned in webinar. Really good question.
Thank you, Pavel. Yeah, fantastic question. To be honest, I've run this on an old Pentium 3 machine with 8 gigabytes of memory. It is a bit slower, but that machine is about 15 years old. The software itself operates according to the processor power that you have available. You can go into the settings, and under the settings, you can add more cores if you have the licenses to do so, and it will run faster and more efficiently on any standard machine. Be it a laptop or a desktop machine. And of course, if you have compute farm capability, we can break out that problem and run across multiple cores. I've seen customers run designs that sometimes perhaps take 3 hours on an 8-core machine, running 5 minutes on a multi-core farm that might have perhaps access to 96 cores. So that speed and that time delay is dependent upon the processor power you have available. To be honest, I would say use the machine that you buy for your children for gaming. Those machines today have fantastic memory and core capability for processing 3D gaming software today.
Okay, thank you. Next question. Are these tools available for a student's license, or do you need a commercial license?
No, we don't restrict the student license at all, Alex. You have everything available to you. Through the Cadence Academic Network, we do ask that the university signs up to teaching with the tools, and then that university domain can be made available for students to download a local license to their own machines. They're not limited. We do have to you do have to request clarity because of that being a separate Cadence tool, but all of the AWR platform features are available in the student license. They typically run for 6 months at a time, and they require you to be a current student at that registered university with a university domain email address. That's how we monitor and maintain that. So when you become a commercial engineer, you cannot take your student license with you, I'm afraid.
Great. Next question is, sorry, just to come back to this previous question, please, if you are from the university, write to us and we send you the needed forms which you need to fill out and to get the free licenses for AWR for educational purpose. Yeah.
Yep.
So the next question is how to define frequency-dependent dielectric constant value in AWR.
Yes, indeed. So when we're defining, and hopefully I'm still sharing my screen, when we're defining the enclosure, the dielectric properties of the materials themselves, we set the grid size, but also the materials. If we wanted to, we could make this property a variable. That variable, we can then hijack the frequency of the simulation and adjust that variable. So if it changes with twice the frequency, we put that in a simple equation, and that value is applied here for the permittivity as we do the frequency sweep. It does rely on the user, Harry, there to know the relationship between frequency and the variation in permittivity. In many cases, for board material in the schematic diagram, so if we had a new schematic, we have under the Elements web-based libraries a lot of substrate vendor materials. And what those material vendors do is they often, so for example, if I find Rogers here, they will give you the ability to simulate with a particular board material they make available. So 5880 is available in these thicknesses with these tolerances. And the beauty of using that as the substrate definition is that when we drag and drop that into a simulation world, the parameters are already set for yield information and tolerance according to the manufacturer's published data. So if you're using a material that is already available in our libraries, that will come with the yield variation tolerances. They don't give you the variation with permittivity and frequency, I'm afraid.
So you mean that Rogers doesn't give the information of variations of permittivity, or gives?
Not in their library elements. No, that's down to the user to add, because I think all board manufacturers assume a constant value.
No. Rogers for sure, and such producers of high frequency PCB materials, they provide the full information of frequency dependency. And another question, I see that you provide the huge library of materials, but I heard that there is also the huge library of components available of from Modalytics, which is very good connected to AWR, right?
Yes, indeed. So Modalytics is a library where, as a company in the US, they've measured surface mount devices on specific board material, and those component models do vary depending upon the material that you put the device on. So, for example, if you've got an 0805 capacitor on Rogers, it will have a different simulation model if it's on FR4 or if it's on alumina. And what they've done is they've coded their devices with quite advanced models. We do need to come into the software and do file new with library. And that new with library, if we start with the Modalytics library, gives us the ability to have the Modalytics elements inside the circuit element library list. Unfortunately, that is a costed library of parts, because Modalytics do a huge amount of work to measure these devices on that board, and they sell those as more advanced models. So if you want the ultimate in accuracy on your very specific board material with your very specific thickness and plating thickness of track, then yes, Modalytics is the way to go. Thank you
I
for
believe,
mentioning that.
sorry to interrupt, I believe some models are free of charge because there are advertisement agreements with suppliers of these components. And
Yes.
also there is services, so you can ask Modalytics to create models for the components which are important to you. So it's not just a fixed library, it could be enhanced with new components. It's paid service. But okay, thank you for, that's great information. So it was
So
about,
I think, Alex, I think we've overrun quite a bit today. Let's wrap up the webinar there. By all means, if we haven't answered your question, we will have them and email you back some answers. Alternatively, if you'd like to contact Alex, if I jump to the last page there, alex@avature.com. I'd like you to thank you for attending today's webinar, your attention. Please do look out for the survey in just a few moments when I stop presenting. Thank you once again.
Please fill out the survey, and in the meanwhile time, I will try to answer the rest. There are a few more questions just manually in the, and Andy, I ask you also to answer the questions in the box, in the gray box. Okay, we will try to publish them. Waiting for your answers to the survey. Thank you so much for attending. Goodbye.
Bye-bye.